Okay, today and in the coming days, we're going to look at something known as L'Hopital's rule. The rule is used to evaluate limits. Now, it might sound funny that we're coming full circle back to limits, but as you'll see, it uses derivatives to actually evaluate the limits. So we're going to cut to the chase here and just give you the rule, and it's right in front of you here. Let me highlight it. It is this right here. Okay, so suppose that f of a equals g of a equals 0. So we have two function values that are equal to 0, two different functions, but we're looking at a quotient of those functions. Suppose they're differentiable on an open interval containing a. So in the neighborhood nearby, it's a nice smooth curve. And suppose that g prime does not equal 0, i.e. the derivative of the bottom does not equal 0. So here is the basics of L'Hopital's rule. If you're taking the limit as x approaches a number of a quotient of functions, and if it is 0 over 0, that's what that's saying there, then you can take the derivative of the top and the bottom, evaluate that limit, and what you'll get is the same result. So, in a nutshell, it means the limit of a function is the quotient of the two other functions is the same as the limit of the derivative of the numerator divided by the derivative of the denominator. You might have to read that a time or two to let that sink in. It sounds like a new complicated thing, but the reality is L'Hopital's rule is used to make some limit questions actually easier. Now, there's some follow-up to it. So this is the basics of L'Hopital's rule. 0 over 0, if you got 0 over 0 when you're taking a limit, which should sound familiar because if you remember we said that was sort of a heads up that the limit would exist. Take the derivative of the top, take the derivative of the bottom, and then try to find your limit again. I can't stress enough, this is not the quotient rule, so you're not applying the quotient rule here. It's not something that where we're evaluating a derivative. We're using a derivative to evaluate a limit. Okay, so why does it work? You can look into this a little bit more, but here's sort of the graphical description of what's happening. So think about that idea that local linearity, when you zoom in on a curve, you basically see a line. So when we're getting in towards that point, dividing the function values is the same as dividing the slopes. And then, of course, slopes are simply derivatives. You can look maybe a little more in depth at the book. In class, maybe we'll look at a proof. Now, with L'Hopital's rule applying. So the official rule is for this little guy right here, 0 over 0. But there are a bunch of what we call indeterminate forms, i.e. they are undefined or they cannot be determined. And other forms can be changed to match L'Hopital's rule. So if a function, when you go to find a limit, if you have infinity over infinity, it can be rewritten so that it's 0 over 0. Now the nice thing is we actually don't have to rewrite it. It can be shown that L'Hopital's rule just specifically works when it's infinity over infinity also. But there's these other cases that are kind of odd. If we have an infinity times 0 when we're finding a limit, infinity minus infinity, 1 to the infinity power, 0 to the 0 power, infinity to the 0, these are all what's known as indeterminate forms. And some of them you might say, well, they look pretty straightforward, like infinity minus infinity, isn't that 0? But a tricky concept in math is understanding that some forms of infinity are actually bigger than other forms of infinity. So we'll start with some basics. In terms of opening problems, we're going to do those in class the old-fashioned way, and then we're going to look at them after you take a look at this video. But let me show you a couple examples of L'Hopital's rule. Let me actually interject with just a really simple one too. So, okay, so just so we have the idea of it and you can just see it in its most basic form. If you have the limit as x approaches 2 for x squared minus 4 over x minus 2. It's a classic, maybe probably one of the first that you saw in advanced trig and calc. Now what we would typically do is we'd factor and cancel, but if you just check the plug-in, you plug 2 into the top, you'll get 2 squared is 4, 4 minus 4 is 0. Plug 2 into the bottom, 2 minus 2 is 0, so this is 0 over 0, that's called indeterminate form. And so that means L'Hopital's rule applies. So what we can do, we can change the problem. It's still the limit as x approaches 2, but the derivative of x squared minus 4, 2x. The derivative of x minus 2, 1. Now plug a 2 in. 2 times 2 is 4. 4 over 1 is 4. And that would be the same answer as if you factored and canceled. Remember this x squared minus 4 would be a difference of 2 squares. So it would be x plus 2, x minus 2, squeezing in the top there. The x minus 2's cancel. You're left with an x plus 2, and 2 plus 2 is 4. So it works. It also works really as a shortcut on that infinity rule that we discussed in class. Like if you have the limit as x approaches infinity, and we've got, say, a 3x cubed plus 7 over x cubed minus 2x plus 1, let's say. Now we would say as x approaches infinity, we'd look at that and we'd say there's the same power in the top and bottom, so we can use the leading coefficients. 3 over 1 is 3. This is also going to show you kind of a neat case of L'Hopital's rule, that it's reiterative. You can reapply L'Hopital's rule as long as it's still in the indeterminate form. So if I look and I sort of mentally plug infinity in, right now I have infinity on the top, infinity in the bottom. That means I can apply L'Hopital's rule. So I can take the limit as x approaches infinity, take the derivative of the top. It's 9x squared. So we already know the answer is going to be 3 from that shortcut that we have. The bottom would be 3x squared minus 2. Well, if I plug infinity into that, I'm getting infinity over infinity again. So I can take the derivative again. Derivative of the top, 18x. Derivative of the bottom, 9x. Now what's interesting is we could repeat. Never mind, I did that wrong. The bottom would be 6x. Now, if you just at first glance look at implying infinity over infinity again, you're going to have the rule be able to apply again. We take the derivative again, we get 18 over 6, and that reduces to 3, which we expected to be the answer. But I should stress that once you apply L'Hopital's rule and reduce it or change it by taking the derivative, you can simplify whatever's left. So 18x over 6x, that right there just simplifies to 3. And so if you have the limit as x approaches infinity for 3, it is indeed 3. Now, as you may have seen when glancing, the problems can, of course, get way more difficult, right? So we've got a few up here. Let me highlight maybe 1 or 2 of these now, and a lot of these we will work on some of the different cases in class. For example, a little rule that we'll look at is this guy right here. If you have a limit and you have a natural log involved, you can e it to find an answer. So we'll look at that, how we can basically incorporate something we don't like the way it looks. We'll change it with a natural log, find that limit, and then get our answer and exponentiate it with e to get the actual answer. But back to this slide, let's look at one more together. Let's look at the, well, you know what, let's just look at the first one. So if I picture plugging a 0 into that, I'd have the square root of 1, which is 1, minus 1, which is 0. I have 0 over 0. So I can take the derivative of the top and the bottom. So, the top. That's a 1 plus x to the 1/2 power. So the derivative would be 1/2 1 plus x to the negative 1/2 minus 1. Well, that'll disappear. And in the bottom, we'd have a 1. So there's our derivative. So if we take the limit as x approaches 0 of that, well, it might help to rewrite it in root form again. And so we would have the limit as x approaches 0 of negative 1/2 power means it is a root in the bottom. So this is 1 over The half there would bring a 2 to the bottom. It'd be the square root of 1 plus x. Well, hey, I can plug a 0 into that. 1 plus 0 is 1. The square root of 1 is 1. 1 times 2 is 2, and this works out to a half. So look at that. That's a limit that would typically require us to do one of a couple things. Of course, we could rely on technology and use our calculators to get the answer. Or, if you recall, when there's a root, we would do what's called rationalizing, where we multiply by the conjugate, root 1 plus x plus 1 over root 1 plus x plus 1. We do some foiling, and eventually it would work out. But L'Hopital's rule is sometimes a cleaner way to look at it. So we will look at some of the funnier ones in class and go over more of it then.